Welcome to Compute 379. It's a course on compilers being taught at the SFE Burnaby campus by Anoop, that's me. Okay, so let's talk about compilers. This is your traditional view of a compiler. We start off with a program, and in the course of the next few slides, what I want to do is sort of emphasize this notion of the program as a data file that's input to the compiler. And so this file will contain some kind of structure and some kind of characters. And we're going to take these and convert it into running machine code. So some set of bits that's going to actually get loaded into memory and going to run. So for example, if your program was foo.c and your compiler is GCC, you can then type in GCC -o foo, which creates a binary file called foo as the output file and takes as the input foo.c. And so this creates a file called foo that you see here, and then when you run foo and you give it some input, it produces some output, and that's what the compiler is supposed to do. Now, if you look at programs as data, let's look at a case where you have a program and when you run it, the output, so the usual way you think about a program, it produces some output, which is a data file or some kind of output that you can interpret. This is an example of a C program. So this over here is a C program that when you compile it, so let's call it quine.c, and it's these kinds of programs are called quines after a philosopher named Quine. You can pause the video now and go look him up in Wikipedia. I'll still be here. You pass quine.c through GCC, and you create a program called Quine, and you run this program and it creates an output, and the output is exactly the same as quine.c. So the output file that it creates, so this file over here, it turns out is exactly the same string or string equivalent to the original program quine.c. That's a kind of an example to get you started on thinking about programs as data. Another sort of meta kind of reasoning one can do is to think about how we actually write a compiler. So obviously when we write a compiler, so let's say we have a compiler like GCC, well, somebody had to build this compiler. So obviously someone has sat down and written the source for GCC. So GCC is a large project written in the C programming language, and it has to be compiled so that when you create machine code, that's going to be the machine code that is GCC. So just to keep things a bit clearer, let's call this guy GCC1. It's a compiler for the source for GCC, and it's going to create a new compiler. Let's call it GCC2. Okay, so it's the same name because it's creating this program called GCC. And the runtime here would be GCC2 running, taking in programs and producing binary files. So in this case, you put in foo.c, and it creates foo, and it produces some output. Okay, so far so good. This is obviously how it works, even though you may not have appreciated that this kind of meta level compilation is going on. But I want you to get used to this idea. Now let's look at this compiler source a bit more carefully and see what it has to do. So if you look at a input program fragment. So this is an input program fragment, just says printf hello world, and I want you to focus just on this part over here. So if you look at the \n, okay, what that means, the programmer wants the final binary for this program to print out the characters hello space world, and then it should print so it should print HALO world, and then at this point it should insert a new line character. And so what the compiler has to do is to make sure that this happens, because that's what the programmer expects it will happen, right? So if you notice here, it says if C is \, which matches this first \, here, and the next character is n, which matches this n here, then it returns \n. Now if you do this, so let's say this is in your compiler source, right? This is somewhere inside the compiler source. You pass the compiler source through the compiler, and it will give you an error because it doesn't know anything about \n. So when it reaches here, this part of the compiler source code, it's going to give you this error. .\n is not a valid character. And that's because \n doesn't really exist in the real world. What exists in the real world is a ASCII character. So this is all written in ASCII, and there is an ASCII character 10. When you print out this ASCII character 10, it actually prints out a new line, right? So that's what's going on. So how do we fix the, well, you can just return the ASCII value 10, right? So now everything works fine. It reaches \, it matches that. It reaches n, it matches n, and then it returns 10. So it will print out hello world and then the new line. Everything works fine. So let's say your compiler source now is your GCC source, and your compiler is GCC in version 1, and now it creates your GCC version 2. So one trick you can do now, which is kind of counterintuitive, but interesting to consider nonetheless, is to take this GCC2 and replace it. Okay, so now what has happened is GCC2 actually knows about \n's being equivalent to 10. So if you give it a character, so these 4 characters, it knows that it's equivalent because of this code. It knows that it's equivalent. So if I replace it, I can just this new compiler. So the new compiler is GCC2. GCC2, remember, knows about \n, and so when you restore the code to the original, so instead of 10, I just replace it with \n, everything just works fine because GCC version 2 actually knows about \n, and when it comes down to this input here, it will actually print out hello world and then a new line, right? So by magic, we've trained the compiler to know what \n means, and sort of with this iterative process of replacing the binary. So so in the original days of Unix, this is how they actually built the C compiler. They bootstrapped it. Initially it had ASCII value 10, and then they bootstrapped it to know about \n, right? And Ken Thompson, one of the original developers of Unix, thought, well, maybe you could actually use it for something a bit more nefarious, like a bit more, let's say, underhanded. So what they did was, well, just like you have to compile the compiler source, the compiler source also is used to compile lots and lots of other things. So the compiler source here, let's, for the sake of argument, call it the GCC source. We create GCC. and let's call it version 1 again. And this is the version that's running here, is GCC version 2. And the input programs is all of your operating system programs, including the program for login.c. So what login.c does is asks you for your username and your password, and then checks in a file whether your password matches what's written down in the file in an encrypted way, of course. So if you have access to the compiler source, you can actually do something a bit underhanded. You can check if you're compiling the login.c file, and when you do, you can insert your own piece of code here. And that piece of code would be very simple, like if the user is a noob, then let him log in. You don't even have to have any password, else do the same thing that you would have done in the login.c file. So what this lets you do is now the username Anoop has access to every instance of Unix anywhere, right? Because it has to be compiled. But of course, if you are dealing with an open source operating system, then this wouldn't work, because anybody who looks at the compiler source would be able to see that somebody's added what's called a Trojan horse inside the code, and then they would just delete it. But we can do something just like the \n to ASCII 10 idea here as well. And what we can do is, in fact, do one meta level higher. So when we have a compiler source, so let's say this is the GCC source, the GCC source now says, am I compiling the compiler, right? If I'm compiling the compiler, then what I can do is change the compile function so that the compile function is actually going to insert the special handling of the login.c file. So what it says is, if I'm compiling the compiler, then insert the login crack. Okay, so it's sort of one level higher than what we were doing before. And when I do this, I would pass it through GCC version 1. GCC version 1 doesn't have any of this special code to crack into machines, and it creates a machine code which is GCC 2. Now GCC 2, remember, is looking for, if it sees something like compile, it will actually auto insert all of this code inside it. So if you went back to this source which contains this code and remove it, it will actually insert it again. What we can do is have nothing inside the compiler. So there's no special if statement here at all. And so we've restored it back to the original GCC source without any Trojan, right? And that's because if you look at the new compiler, which is GCC 2, GCC 2 is going to create a new version, GCC 3. GCC 3 has the login.c crack, right? So this guy has a special if statement that says, it says check compile and modify it, and what it does is inserts a crack into the login.c compilation process. And now when you compile login.c, the runtime compiler inserts this special if statement that lets a new plugin to any machine. So this is actually all covered in this excellent paper by Ken Thompson based on his ACM Turing Award lecture. And I think it's a good way to get started get started on thinking about the meta level of compilers, that you're forced to think in this meta way for lots and lots of things in compilers. So this is a good example of that.